Welcome to this mini volcanic lecture from the flanks of an active volcano. This is Pacaya volcano in Guatemala. Over the next few minutes, I'm going to tell you a little bit more about the basic concepts of volcanology and introduce a few things which may or may not be familiar to you. So in general, we think of any volcanism or any active volcano as where there's evidence of some kind of heat generation mechanism at depth. So Pacaya is a great example of this one because at night time we can see some nice glow from some lava flows traveling down the flanks of this volcano. Another helpful hint is this gas plume which is coming out of the summit. So as I talk, feel free to have a look around at the environment. That's what virtual reality is great for. So the traditional look at what a volcano looks like is the shield type morphology, our upturned bowl, or our stratovolcano type morphology, our picture perfect cone. We do have an example of that in the background just over there, so if you turn around and have a look, it's just behind the clouds, which is unfortunate, but that is Agua volcano, Volcán de Agua in the background, an example of that picture perfect cone. But in reality, our types of volcano are slightly more complex than that. So this is Pacaya volcano, and it hosts a basaltic magma. So this is our first little next step in the volcanic mini lecture, is what types of magma do we have and how can we split up types of volcanism? So we can think of very broad terms, our high viscosity type volcanism and our low viscosity type volcanism. So at the moment, Pacaya in the background is an example of our low viscosity type volcanism, our basaltic type volcanism. We can also think of our higher viscosity type volcanism, our andesites, our dacites, our rhyolites. And the difference between these two is that they contain these two broad themes, the high viscosity and the low viscosity, is that they contain different amounts of silica. So the lower viscosity volcanoes and low viscosity volcanisms, which generally hold basalts, have our lower silica in them. So a basalt might be around 50% silica inside it. Whereas our higher viscosity volcanoes, our higher viscosity volcanism and our magmas, our andesites, our dacites, our rhyolites, they might have more silica within them. And that's really important because that's what makes a magma really viscous. The more silica we have, the more viscous it becomes. And the next thing we need to think about is what actually is a magma and what does it contain? Well, our magma is our three different components. We've got the melt component, which is the liquid rock. We've got our crystal components, our bits of solid rock, and essentially we've got the gas component. So here at Pacaya, we can see this gas component very, very clearly. We can see this gas plume coming out of the top of the McKinney cone, and that is our evidence that this volcano is active. And it demonstrates the importance of gas at this individual location. Which leads me on to a slightly different definition. So this is the definition between open vent and closed vent volcanism. So at Pacaya we have an open vent, and it's an open vent because the gases can be freely released and emitted at the surface. If this volcano were a closed vent system, we may not see much of this gas being released at the surface at all. Gases behave in different ways at volcanoes and within different magmas. So if you're thinking of it in a basaltic context where we have a lower viscosity, something like water, olive oil for example, if you were to blow bubbles into that, you might see the formation of individual much larger bubbles. And essentially that's the same thing that's going on in a basalt. So we can get the joining together of bubbles starting from millimeter sized or sub-millimeter sized at depth. These can coalesce, grow and expand, depressurize during ascent to form much, much larger bubbles. And that can lead to a range of different styles of activity. So if we've got a basaltic magma with not very many bubbles in it, but we've got a large supply of magma coming to the surface, we might see lava flows. If we have very small bubbles which don't form large enough bubbles to form the next volcanic eruption style strombolian activity generated by gas slugs, we might see passive degassing. So that's what we're seeing from Pacaya at the moment. We are seeing passive degassing from the summit. Other styles of basaltic activity could be lava lakes or lava fountaining as well. On the more viscous front, our andesites through to rhyolites, the bubbles find it much more difficult to move and much more difficult to grow because of that viscous impedance of that gas flow. And that's because of the viscosity. So essentially these bubbles don't mix, they don't grow, and that allows these bubbles to move very slowly. And if it's a closed vent system, so that gas isn't being released constantly, that can lead to pressurization at the summit, and it can lead to smaller scale eruptions like Volcanian eruptions, so very ash-rich eruptions, or it can lead to far larger eruptions, subplinian, plinian, or even the top end member of that, the ultraplinian style of volcanism.